That fascinating talk. Many great videos, very fascinating and interesting. We do have time for questions. And so if, when you have a question, I think there are microphones on either side. Okay. Wait for the mic so everybody can hear you clearly. And if you would, for our speaker, graciously identify yourself first and then ask the question, that would be great. So don't all rush at once. Yes, Professor Peng?
Hello, I'm Stella Peng from...
Is that on? Okay.
I always wonder, though, as you make the various nanoparticles or nanoparticles with rings and all different DNAs attached to it, there are always some variations, though, whether that is in size or shapes. I wonder, with some of the variations in the nanoscale, would that make the interpretations of your results to be have the similar kind of uncertainty that you may expect?
Sure. I mean, there's it's not like that we can make all these structures precise. Even the nanostars, I mean, one has to go from one to the other. They always, after the synthesis, they look different. So you take out the nanostar you like for the Raman experiment, for example. So that's a very important issue that one has to live with that, what you call uncertainty, or with the distribution of sizes, shapes. In some cases, it's very narrow, this distribution. In other cases, it's not narrow. One has to live with a broader distribution. In all the cases where you work on single particles, that's not actually so much of a problem. But if you go to ensembles again and want to make a device which relies on ensemble, then it becomes a very big issue. I agree to that. So also we cannot control that we have DNA sheets like 6 on each gold nanoparticle all the time. I mean, you have like 8 or 4 or 6, and you grab one and try to identify that one. That's a good remark, yeah.
Thank you. Next question. Yes, Professor Van Ho.
Thank you. Michel Van Hoof. You talked about gold, but how about other metals? Like silver you mentioned very briefly. So what is the reason for preferring gold?
Mm-hmm. I mean, for that one has to look into the, let's say, the Fermi surface in the reciprocal let's say grating, because in gold you have a very perfect spherical surface of all these electrons, whereas when you go to aluminum or other metals, then you get some backfolding effects due to the different symmetries, and that makes all these conduction band electron movements more complicated. In silver it's still a sphere, so gold and silver are very similar in that respect and very easy, showing all these nice plasmons. But when you go to aluminum, which can still show you a plasmon, and copper, things become much more complicated by that. Silver is actually, from a basic point of view, better because the dissipation is smaller, so the resonance becomes sharper. And for some demonstration experiments, it's sometimes good to take silver instead of gold. But it can oxidize and degrade, so for purposes like biosensing, where these things have to last for some time, they wouldn't take silver, they take gold, because it's just more inert and will stay for a longer time. So at the end, for these experiments and for these applications, it's the point that silver degrades and all the other metals show more difficult properties. Gold seems to be mostly the right choice.
Okay. In the back here.
I was intrigued by in fact, the pictures that's there of the bacteria and the gold, tracking it. How close can you bring them in almost a kind of a tagging, the same way you might tag a dolphin or something? Can you tag the bacteria and track it, or is it an instantaneous snapshot?
I mean, tag it with the gold nanoparticle?
With the gold attendant.
Now what we do, which is not shown here, because the picture was made before the experiment, so we have the gold nanoparticle in one trap, And because this would just swim away, we have to also fix it in another optical trap. So we have 2 traps and then try to bring them together. And there's a limit that they interact, or that even the light intensity for the bacteria becomes too high. And at that distance, that minimum distance, we try to measure some disturbance induced by the bacteria. We take a bacterium, actually I don't know the name, which turns around this tail at a frequency people know, like 100 hertz. And we just bought a new camera with high speed that we can observe this Brownian motion at high speed. And there we can see some signals at 100 hertz now. So it's kind of showing that we are maybe sensitive to that movement. Would be a new way of just studying these kind of movements of such small animals, let's say. But there are also other possibilities. The more we discuss that, the more ideas we get, and we cannot do all of that. What one can do with this Brownian motion and optical trap.
Any others? I was curious, since I'd done some work in photovoltaics. I'm not sure if you said, maybe you did, I was daydreaming about some other gold applications, but what was the efficiency enhancement by using the gold nanoparticles for the examples you were talking
So
about?
where the antenna effect is used, it was never enhanced. On that, when one just uses
Right.
it, because there the gold acts as inducing many traps for the electrons, and so you get more problems than you get advantages so far.
Right.
For the other cases, one uses the scattering. I think the increase was up to 20-30%,
20-30%.
shown by the Amsterdam group. So that's quite
Okay.
quite remarkable.
Yeah.
Yeah.
I'm not surprised about the issues introduced, since I always think of gold in semiconductors as a nice transistor assassin. Yeah. Okay. Any last questions? Okay, well, then let's thank our speaker one more time. And we have one more thing to do. I'm going to invite our acting president to come back up and present our traditional souvenir.
Thank you very much. Wow.
Thank you.
Thank you so much.
Thank you.
Thank you. Bye.